All right, we're live. This is the Algorithms Mob. Here with Mike and myself, and I don't know. We are finishing up the data structure book. So we didn't get to chapter 14, right?
No.
You were going to do this every day, right?
Oh shit! I did not.
It's all right. That's all right. I'll let you off the hook.
Yeah, maybe next week.
Maybe next week. Let's see. I want to open up maybe this folder here. Seems about right. The shortest path. So was this running? This was running, right? You did this.
Yeah.
It's awesome.
Though I think we just did some copy pasting.
Okay.
That's why we said I was going to do it the whole week, every day.
Oh, okay. Why? Where's this path? It's in chapter 10. Oh, draft there is a folder. All right. Shortest path. There we go. All right, there. Sweet.
Mm-hmm.
So, yeah, I need to better prepare for the algorithm mob. I wake up and my brain's fuzzy. Don't know what we were doing last week.
Me neither. It's okay. It's okay to be in this state. I think it shouldn't put you under pressure.
Yeah, maybe. It'd be good to prepare though.
Yeah.
So I don't know if you want to move on or if you want to redo this.
I think we can move on. Then I think I'll do the practice and try to implement it.
Okay.
Yeah.
So I guess we did the wrapping up. Yeah, so our primary focus has been on how fast code runs. However, we've been measuring how efficient our code performs in terms of time, and we've been measuring that in terms of counting the number of steps. Maybe we've also been measuring it using Big O. What's the name for it?
Big O notation. Complexity. Time complexity.
Time complexity. Yeah, there's a name for like the big how you calculate Big O. I think it starts with an A. I forget the name. It'll come to me eventually when I don't need it. So we've been measuring that time in terms of Big O. However, efficiency is actually measured in two ways. One is time. So one is speed, and one is like how much memory it takes. So different types of data structures consume different types of memory, and different types of algorithms can consume different amounts of memory. So like when we were doing some sorting algorithms, and some of those sorting algorithms were in place algorithms, which means they did not consume any more memory. They didn't consume any extra memory when the algorithm ran. This whole sorting was done in place. Some sorting algorithms need to duplicate. So whatever you're sorting, if that takes 1 gig of memory to store that, if that data takes 1 gig to store in memory, then it will take another 1 gig to do the sorting algorithm. Those algorithms are not in place. They rely upon extra memory to do the sorting. And if you don't have an extra 1 gig of memory in, say, your little robotic toy that you're creating to do this sort inside, then you're going to be out of luck, right? So yeah, so like, it's not that big of a deal on our laptops and computers, but when you start dealing with large amounts of data, or when you start dealing with like embedded machines, you might want to care about memory. And a lot of job interviews, they ask you, they kind of trick you. They try to, they ask you, what's the complexity, what's the, how efficient is this algorithm? And if you just give them a time-based response, you might not get that very far. You want to also think in terms of space, the space-based response too. Not only a time-based response, but a space-based response. Space was just meaning memory. Mm-hmm. So, and you can use big O notation to can be applied to space complexity. So yeah, so space complexity becomes an important factor when memory is limited. Yeah, this can happen when programming for small hardware devices that only contain a relatively small amount of memory, or when dealing with large amounts of data, which can quickly fill even large memory containers. So in a perfect world, we'd always use algorithms that are both quick and consume a small amount of memory. However, there are times where we are faced with choosing between the speedy algorithm or the memory efficient algorithm. All right, so you need to take both into consideration and try to make the best choices possible. Yeah, so for job interviews, always be, if they start getting into like big O stuff and asking you for the efficiency of algorithms, you not only have to be concerned with time efficiency, but you also have to be concerned with space efficiency. They will evaluate you on both. So we can use everything we've learned about big O notation to apply that to space complexity. So let's do this. So until now, we've used big O notation to describe an algorithm's speed as follows. We have n elements of data. An algorithm takes a relative number of operational steps. For example, big O of n means that for n data elements, the algorithm takes n steps. And n squared means that for n data elements, the algorithm takes n squared steps. So the same thing applies. What is this? Big O can similarly be used to describe how much space an algorithm takes. For n elements of data, an algorithm consumes a relative number of additional data elements in memory. Okay, I guess this was for the example of how big O is used for time complexity, and this is an example for how big O is used for space complexity. So if you've got big O of 1 space complexity, that means you don't consume any extra space. If you've got big O of n, that means
I think Michael has joined us.
You think Mikhail has joined us. Hello, Mikhail. How goes it?
Fine, you?
Good.
Good.
Trying to wake
Yeah.
up and dispense valuable information.
Yeah.
So we're talking about, I don't know when you joined us, but we're talking about dealing with space constraints. So this entire book we've been exclusively focused on time complexity. But it's just as important to take space complexity into consideration, especially when you're on a job interview and they ask you for the efficiency of an algorithm. You not only need to respond about its time, you don't not only have to think about its time complexity, but you also have to think about space complexity too. And that gets important when you're dealing with large amounts of data or you're programming for small hardware devices that may only contain a small amount of memory. So we can use big O to describe how much space an algorithm takes up. For n elements of data, an algorithm consumes a relative number of additional data elements in memory. So let's look at an example. So this JavaScript function accepts an array of strings and returns an array of those strings in all caps. So here's an example. It would take Amy, Bob, Cindy, Derek in lowercase and return Amy, Bob, Cindy, Derek all in uppercase. Here's one way to write it. So we initialize a new array and then we iterate through the array that we were given. And for each element in the array, we uppercase it and add it to our new array that we created. And then we return new array. So this algorithm takes in an old data set, creates a new data set of equal size. So this would be big O of n. It has linear space complexity. Because for each element, the original array, you need a new, for each memory, square that the original array took up, you're going to need that same amount to run this. You're going to need that same amount available to run this algorithm. So when we analyze the function in terms of space complexity, we can see that it accepts an array of n elements and creates a brand new array that also contains n elements. Because of this, we'd say that the make uppercase function has a space efficiency of big O of n. And so here's an alternative one. This function that is more memory efficient. Instead of creating a new array, it mutates the original array that it took in. So for each element in the array, it uppercases it and then overwrites that original element in the original array. So because of this, since we don't use any extra memory, we say that it uses constant space. It has a constant space complexity. So it has a big O of 1. And, if you're familiar with Ruby, Ruby has commands that returns new elements. And then usually if we map something, it's got the bang, right? So a lot of its methods have no bang on the end, and that means it returns a new object. And the methods that have a bang on the end mutate the original object, or argument, mutates the original argument that you passed into it. And so here you can see that the one without a bang is linear time complexity. I'm sorry, linear space complexity, and that the method with the bang is constant space complexity. So a lot of times when programming for the web, avoiding the bang is ideal because you don't want to mutate the original argument that was passed in. But you know, if you're programming using Ruby to program and for a hardware device, then you might want to be mutating the argument to space save, to save space in your application. It's just, you know, it's just trade-offs. So you got to take those into consideration. So let's talk about the trade-offs. These are trade-offs between time and space. Yeah, so in speeding up your code with Big O, we wrote a JavaScript function that checked whether an array contained any duplicate values. So our first version looked like this. So let's go over this. I don't remember this. So it has duplicate value. We take in an array, and then it looks like we have some nested for loops. So we're going to start with I at 0, and if I is less than array length, we increase I. Then we do j is equal to 0. If j is less than array length, then we increase j. Then if I is not equal to j and array I is equal to array j, then we return true. So yeah, this is a very so this is big O of n squared, right? Because we got those nested for loops. And then we created a more efficient version, which looked like this. So we has equal to values, takes an array. We instantiate a new array, existing numbers, and then if existing numbers and array I is undefined, then we add existing numbers 1 to the array, else we return true. Well, I think this was for ordered. I think this was for ordered arrays, right?
The second one is what came to my mind when I was first thinking of how to handle duplicate values. Yeah, I will create an array of numbers and check if whatever element of the current index is in the existing numbers, and yeah, that's what I would do.
Okay. Yeah, so what is the effects on space complexity for these two algorithms? They both do the same thing?
Yeah. The first one does not use any memory. The second one uses memory but reduces the time.
Mm-hmm. So how much memory does the second one use in terms of Big O?
The second one?
Yeah.
Order of n?
Yep. Yeah. Yeah, so when we created the second version, we declared victory with the second version, pointing to its time complexity. Time complexity in the second version is Big O of n, compared with the first version up here, which is n squared. It's got those two nested for loops. Indeed, from the perspective of time alone, the second version is better. However, when we take space into account, we find the second version has a disadvantage compared with the first version. First version does not consume any additional memory beyond the original array. and therefore has a space complexity of big O of 1. On the other hand, second version creates a brand new array that is the same size as the original array and therefore has a space complexity of big O of n. So here's a neat little table here. So version 1, n squared, yeah, constant. I'm not going to read that. So we can see that version 1 takes up less memory, but it's slower, while version 2 is faster, but takes up more memory. So how do we decide which to choose? And we can't really decide, right? It's something that you're just going to have to make that decision for when you come to that question in your career. Like if you have to deal with space and time issues constantly, you know, it could be a hard decision to make. It might be relatively easy if you don't have any memory, then you just have to forego the speed and go with the slower version. Or you can look for a different algorithm that increases speed while decreasing space complexity, right? There could be a third algorithm that we're not aware of. So the answer, of course, is that it depends on the situation. If we need our application to be blazing fast and we have enough memory to handle it, then version 2 might be preferable. If, on the other hand, speed isn't critical, but we're dealing with a hardware data combination where we need consume memory sparingly, then version 1 might be the right choice. So, yeah, like all technology decisions, there are trade-offs. There's always trade-offs when making a decision. So, man, that's it. Chapter 14 is short. I'd have liked them to put in a third algorithm here. This algorithm is the best. But, I'm trying to think. I can't really recall right now. I wish my brain was more like a sponge. I just remember everything and I can get at that memory without any issues. What's a sponge? Like a sponge just soaks up water, right?
Yeah, okay.
So if your brain is like a sponge, then it just soaks up knowledge, right? So your brain becomes knowledge.
Yeah.
I was just reading that this nine-year-old boy graduates college. This guy right here. He's 9 years old and he just graduated. He just got his bachelor's degree in electrical engineering.
Oh. So when did he start his studies? Like he was not even born yet.
Yeah. He's a genius apparently. So yeah, he's like yeah, he's already being he's going to go get his PhD now, and he's already got many universities that want him to go to their school. So yeah, he's going to get a PhD in electrical engineering while also studying for a medicine degree. And in CES, they told CNN that he is like a sponge.
I don't believe them.
Yeah, but man,
yeah, maybe maybe sometimes they're true. Sometimes maybe the universities also want to.
It could be. It's I don't know. Yeah, it's hard to rationalize how a 9-year-old could be so smart. But I mean, if your brain works that way, if it's built to work, it just takes in everything and you can have instant recall and you learn quickly, then I don't see why You can't, accomplish that in that short of time.
I do, because for me, I think it took me maybe 4 years to learn how to speak well, and then maybe
only 4
another
years.
3. I will say
I've been learning all my life, and I still suck at it.
at least I could ask for something. At 3 or 4 years, I think I could ask for like something if I need a cup of water, maybe. And then it took me so long to learn how to read. I think I'd be 9 and I'd still not know how to read.
Oh,
So,
wow.
yeah.
Everyone's built differently.
Yeah.
Yeah, I gotta go learn a new language, and it's like, oh man. I'm looking forward to it, but it's just. Anyways, let's see. So parting thoughts. So we've learned a lot. Learned that the analysis of data structures and algorithms can dramatically affect your code and speed, memory, and elegance. What you can take away from this book is a framework for making educated technology decisions. Now, computing contains many details, and while something like Big O may suggest that one approach is better than another, other factors can also come into play. The way memory is organized. Yeah, this is important. Yeah, the way memory is organized within your hardware can dramatically, in fact, and the way that your computer language of choice implements things under the hood. Yeah. So like computer architecture, the computers that are in current use in homes today are based on the von Neumann architecture, and they're very good at kind of like what do I want to say? Like we learned to program for the von Neumann architecture. And then when we start getting into like other types of programming, where we're doing like recursive stuff and even like I don't know, I can't really think, but like you can build an algorithm that is more efficient. I mean, you can build a computer that is more efficient for handling like recursive programming when you start doing lots of recursive algorithms. The von Neumann architecture, it stores the most recently used memory in cache, so you can get, because the idea behind that is that if you've just used that memory, then you're going to use it again really quickly. Plus, when you add like 5 plus 4 that's stored in the accumulator, that's ready to use immediately too. So depending on how, so that's why it says it depends on how, memory is organized within your hardware and which computer language you choose, how it implements things under the hood. Each computer, I think I've mentioned it a few times throughout this book, when I talked about, they said like different sorting algorithms, they all implement different languages like Python, Ruby, C. Well, C, not really C, but higher level languages, Python, Ruby, Java, they all implement the core. They all implement things differently. And when they do implement those things, they always take speed and memory and a lot of other factors into consideration to make choices. And so there's some drawback, like when you're using a particular language, if you use an algorithm from one language and then go to another language and use that same built-in algorithm, you might get dramatically different results, and it doesn't really matter anymore if the language is interpreted or compiled or or if one language is deemed to be faster, or it could be based on the fact that, you know, the way they implemented that that algorithm, how they've constructed it to reach out and grab memory and stuff like that in the computer. So yeah, languages, a lot of languages, you know, they're built to be efficient with the von Neumann architecture. So you really don't have to worry that much about it, but it is something to keep in mind. Yeah, if you want to learn more about that, I can suggest a good book. I don't know the name of it off the top of my head, but it's out on my shelf in my room. It's all about computer architecture and all that, and I think there's discussed his anyway, I'm not going to talk more about this. My brain
It's not a sponge.
It's not a sponge. But yeah. But yeah, so Big O is a good way to analyze your algorithm, but it's not the only way. You know, if you get into more serious stuff, you also have to take how the computer is built into consideration, and how the programming language you're using, how it actually implements what you're doing under the hood. Sometimes what you think is the most efficient choice may not be, due to various external reasons. These external reasons are the language you're using, the computer you're using. So, I mean, if you do search online, you can see that, let's see, computer built for recursive function, maybe, I don't know. I think they built a computer for recursive. Yeah, they build a recursion, but they, never mind, I can't find it. There's a computer built for, anyway, if I find anything, I'll just post it in the Slack channel. Let's see, and the way, blah, blah, blah. Because of this, it is always best to test your optimizations with benchmarking tools. And this can be highly subjective too, because when you test with benchmarking tools, you know, your computer is not only just running your algorithm, your computer is also running all the processes within the operating system. So, I mean, you can get some, if you run large amounts of tests and repeat them and randomize them, you might be able to get some good results. But you know, you gotta keep that in mind. You can't just run one test. You gotta run a large amount of tests with good data, random data, to get some good benchmarks, because my computer is different than your computer. I'll get different results than you. Plus, you know, my computer might stop every half a second to kick that algorithm we want to benchmark off the CPU and run something to update the time on the computer, because the computer is constantly updating the time, making sure that the time clock is always accurate and correct. So it might, you know, kick that algorithm off, run with it because it gets an interrupt, run some more important algorithms that the computer deems. And then once those are done, it will put the algorithm that we're benchmarking back onto its CPU and continue. Right, so that's going to affect the benchmark time. So it's always good to not just run one test, run a bunch of tests in many various conditions. So always take this with a grain of salt too. So there are many excellent software applications out there that can measure the speed and memory consumption of your code. The knowledge in this book will point you in the right direction, and the benchmarking tools will confirm whether you've made the right choices with a grain of salt. So I hope that you always take away from this book that topics like these, which seem so complex and esoteric, are just a combination of simpler, easier concepts that are within your grasp. Don't be intimidated by resources that make a concept seem difficult, simply because they don't explain it well. That's what I was doing last week. I was trying to find Dijkstra's white paper that he submitted for his algorithm. It looks very complex, but when you go through it from a resource that explains it, it's actually quite simple. So you can always find a resource that explains it better, most definitely. The topic of data structures and algorithms is broad and deep, and we've only just scratched the surface. There's much more to learn. So this was a good foundation. So we've got a decision to make, and I think Mike suggested that he wants to go through the what's the book called? Hello? Oh, Mike, you're in the background.
Yeah. So it's the Coding Interviews book.
Yeah, hold on. Give me 10 seconds. I'm gonna go grab it. All right, so it's called Cracking the Coding Interview. And there's a 189 programming questions and solutions. I mean, it's a great book. And I mean, there's still many more things to learn in regards to like data structures and algorithms that would help us solve a lot of the problems in this book. So I think it would be good. I mean, if this is what we want to do, perhaps we can just start. I don't know. I'll take a look because I've had this book for a while, but I haven't really opened it up that much. Maybe just a couple times. So it's got it organized. We've got in the first part of the book, it actually looks like it does go through data structures. It's got an introduction, it talks about Big O. It instructs you or dispenses advice on how to prepare for technical interviews and behavioral questions and what to do before the interview. And even when you get like an offer and beyond that, it has some advice on that. And then it gets into like the interview questions. So this would be strictly technical questions. So the first part, it covers data structures, such as arrays, strings, hash tables, string builder. And then it gets into linked list, like creating a linked list, singly linked lists. And then it gets into something called the runner technique. I am not sure what that is. It gets into recursive problems, stacks, queues, trees, and graphs. Then it gets into like concepts and algorithms. bit manipulations, bit facts and tricks, choose complement. Do you know what choose complement is, Mike and Mikhail?
No.
No.
Yeah, you probably won't ever need to use it. It's more of dealing with like binary stuff. If you ever do anything with binary, you might need it. Like same with bit manipulation. If you ever do anything with binary, you might do bit manipulation. And a quick example of bit manipulation would be if I start up a Unix shell here. So let's see. So right here, this is my home folder, right? If I create a new file, call it new file. If I do ls, it's got the new file there. If I take a look at new file, so here these are privileges of my new file. It's saying that I can read and write the file. People who belong to my group staff, they can read the file. And anyone else, they can also read the file. Now I can change these with bit manipulation. And this is actually broken up. This negative sign dictates, or this dash here dictates what type of file it is. If it was a directory, like the documents folder, then, it listed everything in the documents folder. But yeah, so here you can see that this is AV is a directory. So that's why there's a D there. And then you can see I can read, write, execute. The groups can read and execute, and others can read and execute the folder. So let's get back into the new file. So now if I want to change the privileges, you can do that with bit manipulation. So I can change the mode. I think it's chmod, which means change. Short for change mode. So I can pass in an octal number. So imagine this is broken up into 3. So there's a group of 3 there. There's for the user, this is the user privileges. And then when you break the middle section into 3, this is the group privileges. And then this is everyone else privileges. Now, if I only want myself to have read and write privileges and no one else read privileges, then I pass in bit. I can do it with bit manipulation, which is, so if we got binary, so if we break this into 3, so if we imagine, let me write it down on one of these here. So, all right, so we got, let's see this, 1, 2, 3, 1, 2, 3, 1, 2, 3. So you can imagine, so these can be bits. So if it's on, then it's set to 1. So right now I believe it's set like this, right? Yeah, so 1, 1, 0, 1, 0, 0, 1, 0, 0. Right, so right now that's the bits that it's set to. So if we want to set it so that only I have read-write privileges, then we want it 1, 1, 0, 0, 0, 0, 0. So we can pass in an octal number to do that. And if you're familiar with binary, then this number here is, so first is 1, then 2, then 4. So if 4 is set and 2 is set, then we've got a 6 here. And this is, and then this is equal to 4. And this is equal to 4 in binary, right? 1, 0, 0 is 4 in binary. 1, 1, 0 is 6 in binary. So if I just want me to have read-write privileges, then I would keep that as a 6, and I would change the last 2 to zeros. So we can pass in this octal number 600. So chmod 600. And now when did I not do it right?
File name.
Oh yeah. New file. All right, so now when I take a look at it, so you can see it's set it. So if I want to go back and change it change it back to this, then 100 is 4, so I would change it to 644.
Mm-hmm.
And this would be 644. And now when I look at it, you can see it's back to normal, back to the default setting.
What does an octal number mean?
Octal
It goes up to 8?
Yeah, exactly. Octals go up to 7, technically.
7, yeah.
Because you count 0. 0 is a number. Yeah, so if I want to give myself write privileges also and have everyone else not be able to do anything, you can pass in 700. If I want everyone to have all privileges, you can pass in 777. So if I do 777, that gives everyone all privileges. If I want to take away everyone's privileges, I can just pass in all zeros, right? So chmod 000, new file. And then if I ls this, no one has any privileges. However, me being the root, the super user, I've got privilege to everything on the computer, no matter what. So I can still remove this without the file having any privileges. The super user on a Unix system can still change and has access to everything, right? So it's asking, oh, hey, this file doesn't have privileges. So you want to override this file? And say yes. And then, so if we look at it, there's no file now. It got removed. So yeah, so that's bit manipulation. It's just changing the binary numbers in the computer. Sorry. That was exciting for me. Sorry. Went off on a tangent. But yeah, so 2's complement, that's what we were talking about, 2's complement. So 2's complement has to do with binary numbers. And it's basically if you have a binary number, let's say 11011. I don't know what this number is. But if we take the 2's complement of this is actually going to return its negative, the negative representation of this number in binary form. So we can actually do that in Ruby here. So load up Ruby. So to represent a binary number in Ruby, you type 0b, and then anything you type afterward is a binary number. So if you go 11011, so that number is 27. So if we take this and apply the 2's complement, I believe, how do we do it? In Ruby.
Tilde, maybe? No?
Yes, you're right. I think you are right. So if we maybe we're tilting it. There we go. So negative 28. So that is its 2's complement in Ruby. You might think, oh, it should be negative 27, but in order to account for 0, when you take the 2's complement of 27, it's going to be negative 28. It's always going to be one more and the negative number. That way it can account for 0. That way the 2's complement of 0 is still, oh, here it's negative 1. I'm just lying to myself. Interesting.
Yeah, negative 21 makes sense.
Yeah.
Because I think 1 will be indexed at 0.
Yeah. Maybe, I don't know. It's been a while since I've done anything with 2's complement, but it's basically the negative representation in the binary. in binary form.
Where is it used? Like, how is it important in
programming or
data structures, maybe?
data structures? It's obviously important, Mike. Otherwise, it wouldn't be in the book. There are some use cases for it, but I can't expand on that right now because I haven't really given it much thought in the last year since I've learned about them. But I'm sure, if we go through this book, if we go to that section in this book, let me just see it right now. 113. The computers typically store integers in 2's complement representation. A positive number is represented as itself, while a negative number is represented as the 2's complement of its absolute value. Yeah, I don't think it talks about 2's complement, but doesn't really give us a use case for it. I think this goes right into bit manipulation. I'm sure there are use cases for it, especially when you're doing lower level programming, but generally working with higher level programming, you probably won't ever need it. But Ruby and higher level programs, they always make bit manipulation 2's complement available because they want the language to be able to do they want to make things easy for you if you have a task to get done, right? It'd be quite painful if you had to implement that. Bit manipulation and 2's complement in a higher level language. If that was not available, then it's very easy for them to implement that into a high level language. So they just they do it because they want to provide you with the tools for whatever you may come across. See how much time. Oh, okay. So we're just about done. So yeah, so we can go through this book. Does that sound good? I don't know where we'd want to start off with.
Yeah, I think I'd need to get the book as well.
Yeah.
And get familiar with the content.
Yeah, so that's data structures. Yeah, so concepts and algorithms. So it has some math and logic puzzles such as prime numbers.
What edition are you looking at?
Edition? The sixth edition.
Okay.
Wow, 6th edition. I didn't know there were so many. And it talks about object-oriented design, and then recursion and dynamic programming, system design and scalability, sorting and searching, testing. And then it gets into like knowledge-based. It talks about some different programming languages. So it looks like C and C++ is discussed in a few pages, and then it discusses Java. It talks about overloading versus overriding. So, do you know what overloading is in a programming language?
Yeah, I think I used it in Java.
Yeah.
Where you have like same function name used for more than one function.
Yeah, so I'll just do a quick demo here. So in object-oriented programming, if you've got a class, let's just say ABC, I'm going to type Ruby, even though Ruby does not support overloading. Let's see, Ruby. So we've got class ABC, and then we've got maybe we've got our init method, and we do something in this init method, right? We end. Then maybe we've got another class, the DEF, and that inherits from ABC. We might override the init method to do our own initialization. So this would be overriding it. And then, you know, this class, it might actually also have some other method. It's got something, and then end. And you know what? We might actually, actually, no, actually this doesn't need to have it. So now in our specialized, so this would be overriding, right? So we got a method with the same name. Now for overloading, we would have some method here. It does something. Now we can actually have another method with the same name, but for it to be overloading, it's got to take different parameters. So it has to have different parameters. So this could be a value. So since this takes, so since this method, some method takes one parameter, and this some method takes 0 parameters, then these two methods are different methods in Java. In Ruby, you're going to get, this is not good in Ruby. But in Java, this is totally acceptable. And this is called overloading. So this method is overloading this method because the parameters are different. So you can actually have something, you can actually they can both actually take one parameter, but let's say that this takes a string and this takes a type integer, then now this method is overloading that method because they're both different methods. They both take one parameter, but the parameters are of different types, so they're different. So Java sees them as different methods. So this is overloading, whereas when we do the init method, that's just overriding this init method. So that's overloading versus overriding in object-oriented design. Then it gets into databases, threads, and locks, and additional problems in the solutions. So, looks pretty good. So maybe I'm not going to cover the introduction in that book, but maybe we'll cover something that's along the lines of good problem to solve next week. Sound good?
Yep. Yeah.
And then as we're going through it, and if we come across algorithms that uses data structures or concepts that we haven't really covered, we can maybe take a tangent and cover that in detail. Or if you want to just stick strictly to it, we could do that too.
Yeah, I think it's okay.
All right. Cool.
How we evolve.
All right.
Yeah. Okay.
Sounds good. Thanks, Mike.
Thank you. See you next week.